Hello, my name is Elena Milkai, and today I will help you understand how good is your HTAP system. This is a joint work with Yannis Chronis, Gaffney, Zhihan, Jignesh Patel, and Xiangyao. A hybrid transactional and analytical processing database serves both transactions and analytics. HTAP is a very active research area with a huge flurry of papers and numerous commercial systems like TiDB, Hyper, Single Store, and Oracle DualDB. Despite this popularity, currently we don't have a definition of what a good HTAP system is or metrics that can be used to evaluate an HTAP system. And thus, there is no systematic way to judge how good an HTAP system is or to compare multiple HTAP systems. In traditional OLTP or OLAP databases, the fundamental goal is to achieve good absolute transactional or analytical performance, respectively. In HTAP systems, except for the absolute performance values in each workload, we also care for two more goals that every HTAP system should achieve. First is performance isolation. Ideally, there should be no interference between the transactional and the analytical portions of the workload, though they are executed in the same database system. Second goal is real-time analytics. Except for the small query latency, the other very important aspect of real-time analytics is every analytical query to observe all the updates of the latest transactions so that the query result is always up to date. The goal of this work is to define what is a good HTAP system and then to provide a systematic way to evaluate HTAP systems. To achieve that, our first step is to provide a performance metric for HTAP systems. The second step is to quantify and measure freshness of analytical queries. Both these steps can help us discover how close is our HTAP system at achieving performance isolation and real-time analytics, which we already define as the two fundamental goals of HTAP systems. We then design a new benchmark called HTAP to measure performance and freshness. And we use HTAP to evaluate representative HTAP systems. Let's now move to our first metric called throughput frontier that will help us to measure the performance of an HTAP system. In traditional OLTP or OLAP databases, we have only transactional or analytical clients, respectively. And the performance of an OLTP or OLAP system is typically characterized by plotting throughput versus the number of the clients. However, characterizing HTAP performance is more complex. In an HTAP database, we have both transactional and analytical clients that generate different mixes of clients. For each different mix of clients, the database system generates a different hybrid throughput, which is the pair of the transactional and the analytical throughput. To understand how an HTAP system performs, we need to investigate all the possible client mixes and get the hybrid throughputs for each of them. If we sample all the possible client mixes and push the database system to its limits to generate the maximum hybrid throughputs, and then we map the hybrid throughputs to the 2D space, a graph like this will be generated, where the x-axis corresponds to the transactional throughput and the y-axis to the analytical throughput. And each gray bullet point corresponds to a hybrid throughput value generated by a different mix of clients. This graph shows us how the HTAP system performs in the whole HTAP spectrum, because it includes all the possible throughput values the database system can generate. The maximum hybrid throughputs generate the throughput frontier, illustrated with green in the figure, and it is the metric we will use to measure performance in HTAP systems. And it captures the absolute transactional and analytical throughput values, but also it captures the interference between the transactional and analytical portions of the workload, which are executed concurrently in the same database system. We can calculate the throughput frontier with the sampling method we already described, which is also a very accurate method. However, this sampling approach to create the throughput frontier can be prohibitively time-consuming. In this work, we propose a new method called saturation that can help us calculate the throughput frontier of every HTAP system in a constant number of steps. To calculate the throughput frontier with the saturation method, we need to generate a set of fixed T lines and a set of fixed A lines illustrated by the red and blue dashed lines in the figure respectively. The first step of the saturation method is to discover the number of the transactional and analytical clients that maximize the transactional and analytical throughput respectively. Then we divide the ranges of the maximum transactional and analytical clients by a constant. Here is 5. And for each value, we generate a fixed T and a fixed A line respectively. To generate each fixed T line, we fix the number of the transactional clients and we vary the number of the analytical clients until there is no improvement in the analytical throughput. Same for the fixed A lines. We fix the number of the analytical clients and we vary the number of the transactional clients until there is no improvement in the transactional performance. With this method, we are able to generate the throughput frontier by computing the hybrid throughput values of only 36 client mixes, which is extremely faster than the sampling method. Now that we have calculated the throughput frontier, let's see what are the most common patterns and their interpretation. But before that, we need to introduce a set of auxiliary graphs, the throughput, the proportional line, and the bounding box that will help in the analysis of the throughput frontier. The proportional line, illustrated by the blue dashed line, is the line drawn from the two extreme points of the throughput frontier, and it represents a relationship of linear dependence between the transactional and the analytical throughput. The bounding box, illustrated by the red dashed rectangle, is the rectangle formed by the max points of the throughput frontier. The bounding box represents independence between the transactional and the analytical throughput, and ideally it is the throughput frontier of a system that achieves perfect performance isolation. We consider three general throughput frontier patterns. The first pattern is the throughput frontier close to the proportional line. In this case, any increase in the transactional throughput is accompanied by a proportional decrease in the analytical throughput and vice versa. In such a database system, transactions and analytics share resources. The second pattern of the throughput frontier is the above the proportional line and close to the bounding box. In this case, an increase in the transactional throughput may have minimal impact on the analytical throughput and vice versa. HTAP systems that exhibit this behavior are attractive for their performance isolation. The third pattern is a throughput frontier below the proportional line and close to the axis. This throughput frontier shows negative interference between the transactional and analytical portions of the workload. It is an indicator of poor HTAP performance and may indicate contention for resources in the system. A real system may exhibit a throughput frontier with any combination of patterns. Here we separately consider each pattern only to build intuition about the throughput frontier. In general, the less desirable throughput frontier is the one below the proportional line and close to the axis. It will be better to have a frontier close or above the proportional line, and ideally you want a throughput frontier that is close to the bounding box. To sum up, the throughput frontier can quantify absolute transactional and analytical performance, can indicate isolation or interference between the transactional and the analytical components of the workload, can diagnose performance issues, and can discover the architecture design of the HTAP system. Let's now move to our next metric called freshness. Some database systems may choose to sacrifice freshness for better transactional and analytical performance and vice versa. But the user of the database system cannot tell if the analytical queries are always using fresh data. In this work, we quantify freshness and we provide a method to measure freshness in every HTAP system. Our freshness metric extracts the recency of the data snapshots used when an analytical query runs. For example, in this figure, we have three transactions, the T1, T2, and the T3, and an analytical query A1. The figure shows also the commit time of each transaction and the start time of the analytical query. In this scenario, the analytical query can only see the changes made by the transaction T1, but not the changes of the transactions T2 and T3. Then the freshness of the analytical query A1 is equal to the difference of the start time of the query and the commit time of the first not seen transaction by A1, which in this case is a transaction T2. If the analytical query A1 can see all the changes of the three transactions that committed before the start time of the query, then the freshness of the query is 0. Here is also our mathematical definition of the freshness. Measuring freshness without definition has two major challenges. First, there is no globally synchronized clock, so we are unable to measure commit time of transactions and start time of analytical queries. The solution is to conduct all the measurements on the client side. Thus, the commit time of a transaction is now defined as the time the transaction results return to the client, and the start time of the analytical query is defined as the time the query is sent to the database system for execution. Second, it's hard to identify the first not seen transaction. To resolve this challenge, we need extra bookkeeping information, since the analytical query, by definition, cannot identify such a transaction. So we introduce auxiliary tables that store monotonically increasing IDs, which will help us identify the first not seen transaction. Each transaction will update these tables with their transaction ID, and each analytical query will read these tables along with their original workload. Now that we solved the throughput frontier and the freshness metrics, it's time to design a new benchmark that will help us extract the two metrics for every HTAP system. Our benchmark called HTAP is a new hybrid benchmark that consists of an analytical and a transactional component. The analytical component is based on the star schema benchmark, while the transactional component is an adapted version of the TPCC benchmark. HTAP is a simpler benchmark compared to the existing HTAP benchmarks, since it has a simpler schema. Note that the throughput frontier and the freshness metrics can be incorporated to every hybrid benchmark. Our source code is available here. Let's now move to our evaluation part. We experimented with different systems and deployments like Postgres for single node and multiple nodes for streaming replication, TiDB with single node and distributed deployment, and an anonymized system X in single node. For the following experiment, we use a data set of scaling factor 100, which is almost 80 gigabytes of data. In this figure, we see the throughput frontiers of the systems and the deployments we mentioned and their 99th percentile freshness score for the client mix 50-50 as extracted by HTAP. For the comparison, we follow a simple rule. If the throughput frontier region of a system A completely envelopes the throughput frontier of another system B, and A has lower or same freshness score compared to B, then A is better. If not, then we need to dig into more details and consider application requirements. So here system X envelopes almost all the throughput frontiers of the other system and has freshness value equal or smaller than all of them. This means that system X has better absolute values for the transactional and the analytical throughputs and better scaling compared to the other systems. In general, system X has the best HTAP performance compared to all the systems. Let's now move to Postgres with the light blue throughput frontier and Postgres streaming replication with the orange throughput frontier. At first glance, it may not be clear to which system is better. The orange throughput frontier is higher and has better analytical values, but the light blue one has better transactional throughput values. Also, Postgres streaming replication with the orange throughput frontier has better performance scaling since the frontier is above its proportional line, while Postgres with the light blue frontier is mostly below its proportional line, and this fact reveals that the transactional workload is highly affected by the analytical workload. Postgres streaming replication cannot always provide fresh analytics since the freshness score is 5 seconds, while Postgres does. Deciding between Postgres and Postgres streaming replication depends on the user's preferences and the application requirements. If the application requires fresh analytics, then Postgres is a better choice. However, if the freshness requirements are not so strict, then the application can benefit from the better performance scaling of Postgres streaming replication. Finally, between TiDB, single node, and TiDB distributed, the distributed deployment seems to perform better. Our method can combine all the information needed to compare different HTAP systems into a small set of metrics, and our visualization of the metrics make the comparison process more intuitive and simple for the user. We experimented also with different isolation levels, replication mode, physical schemas, and scale factors. You can find more details and experiments in our paper. To conclude, in this work, we introduced two new metrics, the throughput frontier and the freshness. Both these metrics can be used to configure a database system and to discover trade-offs within the system. Moreover, they can also be used to compare multiple HTAP systems very efficiently. The lessons we learned in our evaluation is that first analytics come with a cost in the transactional or end analytical performance. And second, in the most of the cases, the transactional throughput is severely affected by the increase of the analytical clients. Our results showed that there is still room for improving current HTAP systems. Thank you.